Hello, this is Mr. Boston. We're going to check out another energy conservation scenario here, and let's go ahead and get started. So we have a little diagram here to help us understand what they're asking for. A 100 kilogram box is moving at 2 meters per second and is pushed with a 1500 Newton force over a 4-meter distance. The kinetic coefficient between the box and the ground is 0.60. What is the speed of the box at the end of this push? Okay, so the first thing we need to do is figure out what types of energy transformations we're going to have and if it's isolated or not isolated. So it says it's moving initially, so we're going to have some K initial. And we don't have any springs. So we don't have any springs, so that's not something we're going to have here. We don't have any change in height stuff, so we're not going to use UG. We do have some friction stuff, so maybe it'd be a good idea to label what we know. This is a mass. We have a VO we're working with, or we have a push force. Let's call that F. Over some distance, let's call this X. Coefficient of friction, mu. We want to know the final speed. That's our goal. Make it stand out. Okay, so we know we have initial kinetic energy. Okay, and then by the time we end up pushing over here, maybe we're still going to have some kinetic energy, but we're going to also have some heat because we're going to be scraping along there, so we're going to have some thermal energy developed. And I'm going to call my system the box and the earth, which includes the ground here. And I'm going to say that this hand is an external environmental factor that's going to be putting in some work right here. It's going to be forcing us to the right, and we're going to be displacing to the right. So yeah, let's go ahead and go with that. So let's start our energy conservation equation here. That basically says it tells us how we get to a final energy state. Well, it depends on how you started plus what you did to change it. And so we do have work in this case. So let's go ahead and write in the details here. We start with a little bit of kinetic energy, and we're going to do some work to that. And that's going to end up with some kinetic energy in the end, plus some thermal energy creation. Okay, and let's go ahead and do one more line of detail. 1/2 mv initial squared plus some work, which is going to be some force times distance cosine of, well, it pushes to the right and the displacement is in the same direction, so that's an angle of 0 between those, so cosine of 0, and we know that cosine of 0 is just 1, but I felt like we needed to write it out anyways. And that's going to be equal to 1/2 m, and we're going to have our final velocity, which we'd like to solve for, and plus some thermal energy. And we need to take a little side trip here for thermal energy here. Let's do it in red. This thermal energy is hot. So thermal energy is basically the work done by friction. So it's going to be friction times your distance that you're scraping. And we're going to scrape distance x here. As we push along, we're going to scrape. Okay, and now we can say, well, friction is just equal to mu times n, your roughness of your surfaces times how hard you're squeezing those two surfaces together. But my normal force is going to be equal to my weight, which is just equal to mg. Let me convince you of that. So I'm going to draw just the forces acting vertically, all the stuff acting vertically on my system. So It's not falling to the ground, so I have a normal force, and I have weight down. I'm ignoring all horizontal things, okay? Now, it's not levitating off the ground or submarining into the surface, so it's going to have an acceleration in the y direction that's equal to 0. What that means is we're in equilibrium. My weight equals my normal force, and therefore we have this. Okay, so let's go ahead and write that stuff out again. E thermal is just going to be equal to my friction, which is mu n, times my distance. Okay, and then I have my normal force is just going to be equal to mg. So I can write that in. So I can rewrite this one more time. Mu, and my normal force is going to be equal to mg, and I still have my distance x. And so instead of thermal energy, I can write what it's equal to here. And so that's going to be equal to all my red stuff here. So mu times m times g times distance. That's my thermal energy stuff. Okay, so at this point, we can maybe put in all the numbers we know. So 1/2 our mass. Here, let me just go ahead and do this. Okay, so when I put all that stuff in and I do my math to isolate and solve for V, I get 8.8 meters per second. That's rounded slightly. And so that's my answer, which sounds reasonable, I guess. I would like to go through and show you my energy bar chart stuff too. So let me do that right now. Okay, so when I take this 8.8 and I plug it back in here and I calculate my initial kinetic energy, my work, my final kinetic energy, and my thermal energy, these are the values I get right here. And let's plot those to kind of show you what happened here. So real quick here, I had no spring stuff involved here. And I had no UG stuff involved here. And now we can plot what we had left, and it's these things. So I had initial kinetic energy of like, I don't know, nothing pretty much compared to my other energies. And I had some work I invested into my system, which was 6,000 joules, like this. And in the end, that ended up being transferred into just a little over 2,000, not quite 3. And my thermal energy, oops, just kidding. That was over 3, that's almost 4,000 for that. So 3,000, so almost 4,000. Something like that. And my thermal energy was just over 2,000. Like this. And so you can visually see what my energy transformations were. I had a little bit of kinetic energy, but it was actually pretty insignificant compared to the work I put in and the other energies I generate. I did a whole bunch of work, and that turned into mostly kinetic energy, but also a very significant amount of heat was generated in that process too because of the friction as I was doing my work. So if your whole point of this thing when you're pushing this box was to give it kinetic energy, it wasn't very efficient, huh? We generated lots of thermal energy because of the friction that was involved. Okay, so I hope that shows you maybe a nice situation for a non-isolated system where you have some work happening and more of a complex system where you have multiple types of energies involved there. Thanks for watching.